Tonight we're going to do another design recap of our second 2023 robot. Um, the concept for FM, we started talking about it pretty much right as championship ended. We started talking about what would be interesting to build for an off-season project. Um, and we designed it basically almost as an entire another build season. So we were able to sort of talk about it through May a little bit, and we pitched around a couple different ideas based on different teams' robots and different concepts that we saw throughout the season that worked well. And really just started to look at if we have all the information about how the game played all the way through the championship, so we saw a lot of robots play the game, how would we go back and build a interesting robot with our resources and the way that we kind of build robots, but also learn some things from other people, try some things that maybe we hadn't tried before, um, and just build a relatively simple-ish robot that we could get together. Partly because we were going to build it during the camp, so we had about 2 weeks in June that we were putting together the robot with some of our veteran students, but also a lot of new students. We had several people doing the CAD on it, so quite a bit of the design was done by multiple people. And trying to get some robot together that we could make work, and then that we could also develop on, so that we could take it to Chuzzy Champs at the beginning of October. And so this was the culmination of that. So this is the final CAD of where it is right now. We're actually still working on it. So we have people working on designing a Cuban take that's partially finished. They'll probably cover a little bit of at the end of today. So this part down here is all new and doesn't actually exist yet. It's all just being in design right now. But the rest of it was built up from the alpha. And then we redid the CAD for FM specifically. So we actually have an alpha CAD for AM that was a little bit different. And we went through and redid all of this. So it was almost like the second time CADing this exact robot, or very similar robots, and we tweaked things to make it a little bit better. So similar to the way that we did it for our other design recaps, we'll kind of go mechanism by mechanism. Starting with the drivetrain, we won't have to talk too much about this. It's very similar to a lot of our other ones. Up through the slide, which moves in and out to allow us to score on the top nodes. Then the arm joints and how those work, especially the kind of this pivot inside here. This has a lot of details in it. And then the intake as well up here at the top. So I think we have the drivetrain open. Let's switch over to there. So drivetrain basically includes everything that isn't part of the scoring mechanism. So we go ahead and had to mounted our like camera mounting rails and things up here. Any of the protectors and the actual like mounting rails for the whole rest of the upper assemblies are all part of drivetrain for us. So I can hide the bumper, or the belly pan cover, and some of the bumpers. And so we can see kind of what the drivetrain itself looks like. We actually built this on top of our practice bot for X-ray. So we didn't reassemble this drivetrain. So this was already assembled for us during the season to be our 2023 practice bot, swerve drive, belly pan, all of that. So this is all identical to X-ray. There are a few minor differences in terms of like the sensors that were used on it and a couple other things. But for the most part, these robots are the same for their actual drivetrain, but everything above that is very different. One of the biggest things that we changed and kind of added as our development was this mounting rail that runs across the top of it. And so what this lets us do is it lets us have a mounting point out here next to the swerve modules, kind of in the corners, which is really hard to do because they're basically open if you try to mount all the way below it, and you're ending up having to stick up really high to get above them on the MK4Is because you have the whole swerve module gap here. So it's pretty difficult to mount in the corners. So this frame at this height, which should be about 2.5 inches above the other frame. Yep, so it's 2.5 inches. So that gives us a place all the way along that we can mount plates to on the outside, and also importantly on the inside. So you have some options here with how we want to design and mount our mechanisms. And so it gives us a lot more freedom than if we were solely trying to mount to these outer main drive rails. It also means that we can replace these pretty easily. They're not too difficult if we, for some reason, like we actually did have one bend that we didn't replace in season because we didn't think it was that bad, but we could have replaced that rail a little bit easier than it is to replace the entire drive rail down here. And so we like this concept worked pretty well. Our setup just used 4 laser cut polycarb plates, 1 on each side, kind of holding up the middle. And then we had a standoff in the corner to specifically hold that. The rails themselves were bolted together. There's a tube insert in here, and a bolt slides in there to bolt into it. This worked okay. We may work on having some other... We may look at trying to put a gusset across here, maybe across the bottom down here, to hold it together a little bit better in the future. We had a little bit of play and things moved around more than we would like. That gets a little close to where the swerve modules are. It makes it a little tricky possibly to take some things in and out, so we may still have to look at that. But overall it worked pretty well, so we're probably going to do something like that again if it fits our design scheme for 2024. This is definitely easier to work with than some of the mounting on X-Ray that we had, like the plate come up and try to support the elevator rails above the swerve modules. And we ended up having a problem with those. Those we like sheared through during the off season. This rail setup is definitely nicer than that. This also gave us a place for handles. So there were 4 handles. The one up front got hidden. But there were 4 handles on the robot. Made it very easy to lift the robot on and off the field, move it around as we needed to in the pit, take it to and from events. Having some designed-in way to lift the robot is very, very helpful throughout the season. And just it's somewhat of a nice to have, but it is extremely nice to have as you're going to be working with that robot for, you know, multiple months. Being able to pick it up easily is very, very handy. The other thing that we did that we're going to consider drivetrain is our camera rail back here. So we basically just stuck tube just 1 by 1 again with simple gussets going up from the mounting rail. And because we have that mounting rail here, we're able to gusset to both sides of it to support it. It would have been really hard to get a tube here if it was just above the swerve module. There's no easy way to do that. It would probably be brought in somewhere here, and you have like a really big plate, and then you don't have anything supporting it on the inside. So that mounting rail, again, helps a lot with being able to have this supported structure back here. And so this was basically just used for electronics mounting. It gave us a little window to be able to slip the battery in and out of nicely. It gave us a place to mount the radio. The robot signal light was mounted up here, and then also all of our cameras. So we had a Limelight 3 that was used for game piece detection. So it's angled down and pointing out and towards the front of the robot. So it was able to see cones and cubes on the ground, and using the Google Coral and some AI image processing, it can actually decide if it's a cone and then tell us the center of the cone so it can track to it. So the autonomous modes that we were running at Remix and Chezzy Champs, we're actually aligning to those ground cones to let us pick them up reliably. And so that worked quite well. And then to the robot right of the game piece detection Limelight, we had a Limelight 2 that we used for node detection. So it was either doing April tag detection for the cubes, so it was seeing where the April tag was and aligning us center onto that node, or doing reflective tape detection for the cone nodes, and allows us to align for that too. So in autonomous, we were using that to align, and then sometimes during driver control, we were using that to align as well. And then below it, the CAD model for the camera is not here, but this mount is where we have the driver cam. So we have a nice fisheye driver cam that lets us see a good amount of the ground for intaking. So if the robot's facing away from us and we can't quite see where the intake is, we can look down through the camera to see it. And then it's wide enough to where we can see some of the loading zones and things too, to make sure we're aligned there. And then so those 4 cameras are all used for the actual robot and during the match. And then we for Remix, we mounted a GoPro mount And so we ran a GoPro on it for basically every match of Remix and Chesney Champs. We tried to have GoPro footage. This position worked really well. We were able to see the full intake at pretty much any of its loading spots and while we were scoring. And so we used it both to have cool media afterwards because we have that robot view, but more importantly, we're using it as a diagnostic tool to where we can tell, are we aligned to the shelf properly, are our heights right when we're on the field, are we aligned to the loading zones, anything like that. We could see very clearly in the GoPro footage how the cone was coming into the robot, how we were scoring it. So we were able to look at that for basically every match and see how the autons were running. Like having that view was just very helpful to a lot of our tuning throughout the events and trying to make the robot better. So that pretty much covers Drivetrain, other than bumpers, which the mounts for those only partially exist in here. We can see kind of what we did, but basically we had C channels and spacer plates that were wood screwed into the plywood, and then we had pins that would drop through the 1x1 into the 2x1 and hold everything together. The actual pin setup and bracket setup worked well enough. There were some times where things started getting a little bent and we have to like drill through the hole a little bit to make sure everything stayed aligned. Our biggest problem though is we relied on the wood screws into the plywood. And so at Chesney Champs in one of the playoff matches, our bumper was knocked off. It was knocked off because it took 24 wood screws that were in both of these plates. It was actually the back one. It ripped them fully through the plywood, and that's how the back bumper was able to come off. So if we do anything like this again, which we're planning to do something similar, we will have bolts that run all the way through and have a nut on the back side so that you can't shear through, you can't just rip the wood screws out. It would be much harder to take a bolt all the way through it. So that will help improve the bumper reliability a little bit. We're still going to look at ways to improve this setup to make it easier to both create and mount when we're at events and things. The pin setup and everything did work as expected. It kind of allows us to make bumpers without having to CNC anything because you don't have your corners. You don't have to worry about the exact dimensions to get your corners. It makes it very easy to wrap and unwrap the bumpers to replace noodles or to replace fabric. Or to replace numbers. Like if you just have to replace a whole side, that's a lot easier than replacing the entire bumper fabric and rewrapping the whole thing. As the seasons get longer, we were just finding we had a lot more tears and rips and cuts through the bumper, so it ended up more and more tape, where if we just have a single segment, ideally we'll be able to just rewrap that one segment with fabric, apply new numbers, and be good to go again for our next event. Okay, so getting up to the stuff that actually scores points. The upper structure and even the mounting rail setup was all inspired by 3538's robot, the Robo Jackets. They built a robot that has a pretty similar structure in that it has the slide that's basically at the angle of the grid. So our scoring positions for the mid-level are the arm scoring positions are the same as they are for the top. The only difference is whether we extend the slide up to the top level or not. So that makes it programming that very easily, as we basically just have the mid nodes ready to go, and then we just tell the slide to extend up, and that's what we use to score in the top. The slide mechanism is pretty easy to build since it's only a single stage linear mechanism. You don't have to worry too much about like belt looping and wrapping or anything. You just have this one continuous belt down here that's powered by the motor, and that works very, very easily. We don't have those same problems we had with the elevator on X-Ray. Whereas it wrapped, you had like different pulleys bending and stuff because there's so many pulleys involved in getting that full continuous loop through all the stages. The rails are fully contained, so you have bearings on all four sides of this moving rail at the front here, so these are kind of stationary, and then you have all four sides down here on this rail, and they all are unable to come apart. So even if your tolerances aren't exactly right, if something happens to one of the bearings or anything, it may not move as smoothly, but it's not able to like fall apart. It can't come out or anything. And so this whole mechanism is able to slide up, and that's what extends us up to the top rail, or to the top nodes. That does mean that our motors have to move with it. So these two motors are there to power the arm. So that's part of like the slide mechanism here at the back, is all of the motor mounting has to be integrated into this rear slide plate. That is what's actually getting pulled up and down. That works nicely. That keeps our weight relatively low when it's actually down, which is most of the match. The slide stays basically retracted most of the time. We had to make sure nothing left frame perimeter, so this was a little bit of a tricky design here when we started adding in this top motor. We had to make sure it didn't pass this back frame at all, while still leaving room under it for the bearing assembly up here. So that's why we got these plates that ended up being pretty funky shaped plates to make this like almost a C that wraps around this whole thing. You can see it in a couple others. So yeah, so you mount it up here, and then we have the lower mounting plates there. And then we also had to stand off this other motor to be able to power the arm itself up here. And so we end up with 3 motors and their gearboxes and 90-degree adapters, all built in right here at the end. What were the other things? Yeah, so all of this ends up just being made mostly out of laser cut polycarbonate. So these main mounting panels down here, the ones that mount it to the frame here, are all just laser cut polycarb. We did end up doing some parts out of sheet metal, so just be able to keep things thin enough. These outer parts that hold the bearing assemblies, because these bearings are just basically pushing out into these plates. We made these out of aluminum so that we wouldn't have any issues with those bearing loads trying to bend these out too much or anything like that. So there are 4 aluminum plates that were made for that specific part of the process. We should be able to open up slide here. I think we have somewhere. Yeah, so we can look at it directly. The other part of it that we did not talk about is actually how the belt connects down here. So we end up with just these pulleys that are 3D printed. So we end up doing this a decent amount where we just print the hex directly into the pulley and it goes onto the hex output of the gearbox. And so that's how it spins. But to actually mount the belt to the slide to get this to move, what we do is we have a bolt that runs through this hole, so that's not in CAD or at the moment, but there's a bolt that runs through here. And so the belt is cut, and it's wrapped around itself and basically zip tied to itself that wraps around this bolt. And so that's how one end is terminated on this mount. The other end is terminated on this shaft, which has a wrench on it. So I actually think it's on the outside here. So I think the shaft's a little bit longer on the real robot than it is in CAD. And so there's a ratcheting wrench here, similar to the ratcheting wrench that we used on X-Ray. It's just a 3/8 ratcheting wrench this time. There's a bolt here that allows it to stop it from rotating. And then we're able to bolt the belt to this hex shaft. And then as we turn this hex shaft and spin it, we can wrap the belt around it to tighten it, so we can tension that belt and get it to where we want it. And then the ratchet prevents it from going back the other way. So the ratchet basically stays on the robot the whole time. It's just a cut-off ratchet, just like the normal tool would be. And we're able to spin this hex shaft to tension the belt up and make sure it doesn't slip at all when the motor drives this pulley, and it pulls it up and moves the whole arm up out of the robot to be able to score in the top nodes. This is the exact same pulley as below, printed with a hex in it as well, and then just spinning and bearings up here. So it has nice smooth motion throughout its whole path. There's no other sensors on this or anything, so this always just starts fully down, so we know where its zero is, and then we're able to move it up a certain amount of motor rotations and get it to go to the spot we want to be able to score on the top node. We have a little bit of extra room, not very much, before we want to go to the top node. We don't drive it all the way into the hard stop. For things like this, for pretty much any linear motion, anytime you can have roller bearings rolling on the parts that are moving instead of having any sort of sliding is going to be more efficient. So there's just a lot less friction when you have these roller bearings here. We could have done the same thing with just like a smooth piece of plastic. There's a lot of plastics that have low coefficient of friction, so they're just very slippery. And we could have mounted one of those up on the sides, especially in the side positions where they're taking less of the load. And it would have worked the same. It would just been a little bit more force for the motor to move it sometimes, potentially a little bit more likely for it to jam. So if you want really consistent linear motion, it's much better to use bearings whenever you can. We were able to do that using bearings that just sat on number 10 bolts. So these are 5mm ID bearings, which is very similar diameter to a number 10 bolt. So these are the same bolts we use everywhere else on the robot. That lets us standardize on tools. So it's a metric bearing, so we have to CAD in the spacing a little bit differently. But it's not too different than standard sizes anyway. So the 0.063 is pretty close to 0.0625 or 0.625. So it works out pretty nicely on the dimensions everywhere. These inner ones that weren't going to be bolts can be a little bit different. So I think these ended up being 6mm shafts. They might have been quarter shafts, actually. I'm not sure. They're either 6mm or quarter, and then 1/2-inch OD bearings on them. But since they're not bolts, it's okay because we're going to have to buy special pins anyway. They probably were quarter. And that seemed to work pretty well for the bearing setup. We'd have to play with it a little bit to get the tolerances right, to make sure it wasn't too tight or too loose, but nothing too bad to get it to work out. Up here, we did have to have some countersunk hardware because we were trying to make sure we weren't having our bolts run into the chain at all. So there's a few places where it'll get very close, where it basically rubs right across some bolt heads right here. So we're able to countersink those in and get those out of the way of the motion. So some of those are things you had to find a little bit late as we're trying to save every little bit of space we can in places to get the design to work properly. So a lot of those little tiny things happen like that where those had to get swapped to countersunk, but that's easy enough to do. And that's still within our standard fasteners that we already own and things like that. Okay, so that pretty much covers the slide. The arm is where we really had to put a lot of thought into how this robot would work. This was, like I said earlier, this was modeled after 3538. Their robot had a very similar slide, so we were able to copy a lot of their geometry directly. Still had to move a little bit. Our robot's a little bit different length. Things were at a little bit different height, so we still had to move things around. It's definitely not the same. The way our parts being polycarbonate and things were different than theirs. But the concept was very, very similar for the slide. For the arms, we ended up needing to change that concept quite a bit because we were changing our intake. So their intake was a horizontal roller setup, almost similar, more similar to what X-Ray did, where we had a wider amount of rollers or wheels, and you suck the cone between them and the cube under them. So a lot of teams ran similar things to that year, or this past year. And so they used what's called a virtual 4-bar to control their arm setup, to where their arm is always basically, their intake is always at the same angle to their frame, even as the arm moves through its motion. So here it gets a little bit weird in Onshape, but let me see if I can get something close. Okay, so if their arm was always pretty close to horizontal, as this arm moves through, try not to move the slide, it's always going to stay horizontal. So their arm basically only has control of this one joint, and so they can move everything up and down. It's about as far as you can get without moving the slide. Okay, so they can move the rotation everywhere, but then they don't have independent control of this axis to move it back and forth. So we need to figure out, to be able to use the horizontal intake the way we wanted, we knew we needed to be able to control it independently so that we could like come down into this position and angle it down. Not quite that much. Should figure out a way to stop the slide from moving. There's only so much you can do here. Okay. Well, we wanted to figure out a way to move it down so that it could intake cones off the floor. Not quite that much, as that's clearly into the robot. So, there we go. All right, that's a little closer. So we wanted to be able to intake cones from the floor. We wanted to be able to intake cubes from the floor. We also wanted to have some extra control of positions while we were scoring, and while we were getting objects from the single substation, which meant having like this intake pointed up a little bit so it could catch the cones as they were coming down the ramp. And even while we were doing the double substation and things, we ended up tipping down a little bit. Things the robot can't do. It can't get into some of those positions. Okay. Yeah, we'll figure that out later. But so being able to control that independently is the important part. Sort of get back in something normal. All right, so back in default normal position. On-shape name positions are very handy when you have things that can move around, because you can set them back to the position you want. Okay, so being able to get it into an independent position meant we knew we were going to have 2 motors, so that's why we have this motor on top and this one down here on the back, and we have 2 different chain runs running to this central pivot. And so the first one basically controls the shoulder. So this one down here that's stood off from this plate, it has a sprocket that's run, and sprocket and chain that runs very close to the arm here. And it gives us, this motion is all transferred directly into this arm. So when this sprocket moves, this first arm is what pivots around. So these bolts here are bolting in through the sprocket, in through the spacer, and into this 3D printed part that's in the arm. And this whole arm is not actually in contact, or it's not actually rotating with this shaft at all. So if we look inside here a little bit, let me see if I can hide that, and our spacer here, we can see that we have this bushing that is just a round hole on the inside. So there's just a round hole here. And so the max pline shaft, which is this one, even though it has this like flower pattern that allows it to kind of act like a hex shaft and be able to have things that key into it and spin with it, when we just have it on that bushing, it's just able to rotate around it freely. It doesn't really matter how this is rotating. It doesn't affect how this arm is rotating in relation to it. So mechanisms like this, when we have 2 different things rotating on the same axis, right? They're rotating on that same pivot point or rotation point. Those are called coaxial. And so they're sharing this axis to be able to transfer mechanical power through something else that also is rotating as well. So in this case, this sprocket gets drilled out, so it has a much bigger hole here, so it doesn't touch the max spline pattern. There's a spacer under it, and the spacer between it here. And then this arm is just spinning on these bushings to freely rotate without worrying about how this max spline is spinning at all. So what we actually do care about, and the reason we use this max spline, is to be able to have the sprocket over here that's driven by this top motor. So this motor and gearbox has the smaller sprocket. It drives this bigger sprocket, and it rotates it. But we need to be able to have this rotation match up with this rotation so that then we can power the actual intake arm way over here. And so it does that by this sprocket having that same max spline pattern in it. So it has that like flower, and so the max spline sits nicely into these little grooves, and so when this sprocket rotates, the whole shaft rotates and comes all the way over and does the same thing over here. So this whole shaft rotates with this sprocket, and so now we have independent control of these two sprockets independently from this third one and this whole arm assembly. So we can set this arm into a lot of different positions when you have the ability to rotate both things independently. So something like that position is what we use for our single substation loading, to be able to have a cone drop down and get caught in here, or have a cube come down and get caught in here. And we wouldn't be able to do that if we had used the virtual 4-bar setup that kept this at the same angle the whole time. The other part of this, so the way this whole pivot is actually mounted to the slide, is we have these 2 1/4-inch aluminum plates. We wanted to make sure that these were going to be rather stiff and not bend anywhere, since they had the whole arm hanging off of it, basically. So we made these on our router, and we routed out the hole patterns and the holes for the bushings up here. And then we have these bushings that the max spline slides into and can spin pretty freely in. Both of these motions are all pretty slow rotations, so we're not spinning very quickly like we would for our intake that has to spin pretty fast to grab the cones and the cubes, or anything like a launcher that has to spin really fast to like launch a ball out in some seasons. So as long as we're spinning slowly, using a bushing where you do have that sliding contact, where there's not anything, there's not like roller bearings or anything specifically rolling in here, but the bushings are pretty good in that they can take a lot of load without breaking. And for slow rotations, you're not going to generate a lot of friction from them anyway. And the motors, since they are running so much slower, they have a lot of torque to be able to overcome any of that friction that is generated because it's just sliding and rubbing. We do put a little bit of grease on them when we first assembled it, but most of it, the bushings themselves are designed to sort of self-lubricate. They have oil impregnated into them. And so as they rub, they'll get a little bit smooth and make that motion work pretty well, even if they are tight, and even if they are just like sliding against it. The other parts of this are mostly spacers, where we have some 3D printed spacers in here to keep everything like stacked up the way we want. And then the part of this that we added was, as we built it, originally we just had this, we just had the shaft going through it and the max spline, and we just had the snap rings on it holding everything together. And we didn't have this hex shaft that's here or this cap. So let me hide those and see what the original assembly looked like. So this is basically the original assembly. And so it worked pretty well. So we were testing with it. Everything was going fine. But as we started getting closer to our first event with it to go to Remix, it started loosening up a little bit. And so you could like wiggle the arm. If you like grabbed the arm and tried to like bend it back and forth, you could wiggle it a little bit, and you could like you could make a gap between the snap ring and the sprocket. And so it just wasn't as stiff as we wanted it to be. It also caused it to be able to fall a little bit easier. So if you just brought the arm up and you set it there even in brake mode, it would fall sometimes, or not, like, especially when the power was off, it would just fall. Even in brake mode, sometimes it would do it. So that made it a little bit harder to do our robot setup the way we wanted to, and things like that. So what we ended up doing was figuring out a way to be able to compress these two sides together. So we wanted to be able to basically like sandwich them and bolt them somehow. And we rather quickly realized that if we ran a hex shaft through the middle that was a little short, so it doesn't actually reach the end over here, right? So it's cut off a little bit before it's at the end. We made a little 3D printed spacer that fit inside of the max spline, and had a, and then this hex shaft was tapped here, so there'd be a bolt and a washer that fit around this whole end here. So we could bolt this side basically to the entire shaft and everything and hold it together. We would then have this end cap that didn't touch the max spline on this side. So I make it transparent. Oops, a little too transparent. What happened here? A little too far. Oh, you can kind of see it. Okay. So there we go. So there's still a gap here to the actual max spline. So we would put a bolt through here into this hex shaft. Oh, that went all the way down. Okay. So it would go into that hex shaft here. And it would be able to basically push this sprocket up against the rest of this assembly, right? So it's going to pull this side in, it's going to push this, and will generate a small gap between this snap ring and the sprocket. Is basically what we're trying to do, to be able to sandwich that whole assembly, and we'd be able to tighten it just by tightening two bolts. We'd be able to get this whole assembly a little bit tighter, to where this whole thing almost acts like a slip clutch. So if you, as you tighten it too much, you can get it to where it becomes really hard to move this at all until you overcome the friction generated by like this cap pushing on here and all of these being squeezed together to their next spacer and everything else. So as we squeeze those all together, we just build up the friction in that system a little bit more. Everything gets tight so they can't wiggle back and forth. And they also let it so the motor just has to be the thing that moves it, and gravity can't move it as easily on the arms. And so that worked pretty well for our setup. We were able to implement that right before Remix, and that ran without issue at all through both of our events. And we would definitely do this again on any of the max spline joints, anything like this if we could. We would build up some sort of setup like this. And this is just a couple 3D printed parts, and a quickly cut hex shaft that was tapped on both ends, to solve that problem for us. The other thing that we did that's not in CAD is we were worried that we might possibly bend this max spline. We messed up one of the ones right before one of our events. We found that we did damage part of the max spline where we kind of like bent it in a little bit. And so we replaced this max spline, and we went ahead and put a 1-inch OD tube that fits directly inside of it. So this round part in here has a 1/2-inch radius, so a 1-inch aluminum tube will fit inside of it and kind of support these walls. So we put a relatively thick wall, I think it was 1/8-inch wall, tube running the whole length of it, just in case we started seeing any of that other damage where we might bend in any of these or collapse them, as we're transferring so much torque just through the max spline there to the other, to the rest of the arm. And so that lasted and held up very well through Chesney Champs as well. Yeah, so to reiterate kind of how that motion works, motor down here runs to this sprocket. This sprocket doesn't have any bolts in it or anything. It's just rotating this spline shaft that's running the whole length. And the same thing happens over on this outer one. So it's attached to the spline shaft. So these two are always staying in sync to each other. And then this sprocket is running down, and it powers this other one that's bolted to the intake arm. Let's see if I can bring it back up, make this a little bit easier. All right, so these get bolts running through them again, so similar to how this main arm was bolted to that middle sprocket. This sprocket will have, it had some countersink bolts. Ooh, it's hard to find that viewpoint that works. So it had some bolts running into the arm for it. So the sprocket doesn't move here in the assembly, but it would bend those like 6 holes here, or some version of those, would have bolts into it that we were able to put, yeah, so these holes right here, these bolts right here would be bolted and nuts into this arm. And so that's how you're getting that motion to actually be able to move the intake, is all from those 4 sprockets, starting with the small one, up to the big one, over here, and then to here. And so that lets us put the intake at whatever angle we want, just by commanding that motor to go whatever angle we need. We also ran some of the wire management for this. We ran the wires inside the tube here, ran it down and then out of a hole here, and then up through, and we actually, in this case, routed it inside this max spline. So it went through, and then once it was out over here, we were able to put it back in and actually into this tube as well to hide the wires a little bit more. This cover we made so that when the wires actually passed this chain, they weren't getting cut on it. We had that happen on the Alpha robot a little bit. They were getting dragged across this chain and getting worn down and cut slightly. So we made a little 3D printed cover to avoid that. That seemed to work pretty well. These 3D printed blocks are here to be able to support the bushings again. So we have these same type of bushings that we used up at the top. We have them down here so that we can support this part of the shaft that's going to move independently. So this is spinning inside this tube, and it's spinning attached to this tube. The max spline itself actually fits inside that pattern that's cut into the tube. So this is max spline tube, so it comes with that like flower pattern cut into it already. So we buy it from Rev directly like that. And so it's very, very easy to move a 2x1 that already has that pattern in there. You just stick the max spline through it. We did make sure the sprocket was fully bolted to it as well, but with the sprocket having the max spline, the tube having the max spline, that whole joint is very, very stiff, and worked quite nicely for us to be able to control that angle. So yeah, so that's pretty much how the arm works. And then the last main part of this robot is the Cuban cone intake. And this was based on several other teams who made intakes similar to this. So this is similar to 1114's intake. This is similar to Strike Zone. There were quite a few robots that had smaller wheels on the outside and then these 4-inch compliant wheels to the inside, to where you could grab a cube sort of between the front ones, but then you could pinch a cone back through the middle, back through the rear ones very nicely. One of the main goals for this robot as we were designing it was we wanted to be able to do a multi-cone autonomous mode. And so that meant we needed to be able to very precisely know where the cone was so that we could align the robot in autonomous and place it on the node. And so the intakes like this worked very well for that. We also saw that they were working very well for loading the cones from the double substation. Since the cones don't slide around and get pushed around as much as from the as the cubes do, they're also doing really good ground loading of cones, which we wanted to be able to do in autonomous. And again, have that like precise position where we knew where they were. And so this design worked well for us. We played a little bit with the gap here. I think we made another version that made the gap a little bit smaller so that we could pinch the cone a little tighter. This is the tighter version in CAD now. Late on, we added additional wheels so that we could hold the cube a little bit better. So we had these top wheels that weren't there in the first version, so we could hold the cube a little higher and better. It didn't really affect any of our cone grabbing. Similarly, we added this bar down here that we call the cone bar, and it basically allowed for a cone when it came in to never be tipped backwards. Ideally we want it kind of straight up and down inside the intake, but if it ends up angled forward a little bit, that's fine. If the opening is towards the front, we're still able to score that. We might have to like have the pilot adjust a little bit to be able to get it on the node, but we're able to score it. If the cone is tipped the other way, if the cone, like the opening is faced towards the robot, it's a lot harder for us to score, and we saw that problem in practice. And just putting a bar here fixed it nicely. These were originally 3D printed hex shafts, but we actually broke them when our Autonomous went wild at their very first event at Remix. And then we replaced them with aluminum. And then just a very easy piece of laser cut polycarbonate here at the bottom. Actually, I think we might have even just printed this part too because it's so small. And so that worked well to keep the cone from ever tipping in the other direction. So a couple design features of this. We wanted the motor, since that's the one of the heavier parts of this intake, to be back as close to the pivot as we could. So it's mounted pretty close to where we're going to be moving this in and out with the sprocket, so its weight doesn't affect it as much. If we had the motor weight way up here, the arm motor has to do a lot more to move it around. So the closer you can get your heavier objects to the pivot point, the easier it is for them to rotate around. So anytime you can get the motor farther back, or anything else that's going to be heavy on that mechanism, the closer to the pivot is, the easier it's going to be to move. And so we knew we could just belt it forward, so that was easy enough to make simple motor mounting plate, nothing complicated. Up to a pulley here. As we were making it, we did start seeing a little bit of flex on this plate because we just made this out of polycarbonate, so it could bend a little bit. And so we could have either redone it out of aluminum, but we also knew we could just support the back side of the motor. And so we made a 3D printed clamp that would just clamp over the motor with these two bolts. And that would stop this from being able to wiggle, or any like flex that was in this plate was taken up by that clamp setup here. And so that worked really nicely. We could definitely see ourselves doing that again if there's a time where we need to have a motor just on a cantilevered plate. Keeps that shaft straight, keeps the belt in tension the whole time. So it definitely reduces any amount of slipping that the belt can do. If this can pull at all, you could possibly be able to slip teeth. With it clamped down here, that doesn't happen. This is a pretty common sort of intake form for a decent number of FIRST robotics competition games, where you just have vertical rollers that are opposing each other. So one has to spin. This one would be spinning counterclockwise. This one would be spinning clockwise. And they would just bring the game piece in through the middle. To get that counter-rotating motion, we power one shaft here, and then we have a set of gears that allow us to get counter-rotating motion. So if this was replaced by like another belt, they would still be spinning the same way, either all counterclockwise or all clockwise. But when we have the gears here, whichever way this gear is spinning, this gear is always spinning the opposite, which is exactly what we want for this mechanism. And so there's a very easy way to do that back here, kind of where we already have to have some stuff to stop the cone from coming back too far. It was very easy to put a couple shafts with the gears here, and then we could make it symmetric from there. So our pulleys and wheel alignments and everything are basically symmetric right down the middle of our intake. That means we can use the same belts everywhere, the same pulleys everywhere, and just mirror them across from each other. There's a few standoffs in places to kind of give the whole intake some structure, but we also use the arm itself to come through and help give the intake some structure, since it's all cantilevered off this one side. Having the arm all the way out here keeps the intake pretty rigid and not flexing too much, so it can replace a lot of those standoffs just with the way we were able to mount it here. All the pulleys on the intake are 3D printed. We did use aluminum gears. Actually, I think we ended up using a steel and aluminum gear because that's what we had in stock. Some form of a printed gear could work, especially if you, with all the space we have here, we could have made very tall printed gears to make the teeth really a lot longer and a lot bigger. And those would have probably worked fine as well. But when we can do metal, it's sometimes a little bit easier. The weight penalty isn't that much for gears that small. So nothing too complicated there. We did move everything into bearings just because everything's spinning pretty fast for an intake. We originally had bushings out at the front in the first version of it, but we ended up having some issues with how we were compressing things and some stuff rubbing that caused us some issues on the first version of our intake. So we knew switching everything to bearings would solve it. There's probably ways to solve it. If we wanted to go back to bushings, we could probably make a version that worked. But anytime we have things spinning fast, if we can put it in bearings, it's a little bit easier and just a little bit more, we have a little bit more confidence that's going to stay working for an entire event and for whole seasons. Again, all of these pulleys are just 3D printed. The belts we get from different belt manufacturers, but normally vbeltguys.com is the one we use the most. They're very cheap. These are normally $3 or $4 a piece, and you can get them in practically any size. We'll go over how we do belt calculations in the future. But we're able to basically figure out what pulleys we want, figure out about what spacing we think we need, and then we can calculate the exact belt we can use to match the pulleys and to match that spacing. Everything was done with snap rings, so we did all of those on the lathe. That works because then you don't have a bolt that can possibly come out. You don't have a shaft collar that can loosen. You'd have to basically like break part of the metal here to be able to pull this out, unless you have the snap ring pliers that can insert into these two holes and then spread out the snap ring to be able to pull it over the hex shaft. I think when we did make the change for the taller wheels, we did end up just swapping in a hex shaft that we tapped and put number 10s in. In season, we would have eventually replaced that with a snap ring shaft too. There's also times where it makes sense to, since we're almost all of these shafts would have a hole in them because we're using the 1/2-inch rounded hex that already comes with a hole that's able to be tapped to 1032. A lot of times we will just tap that, put threads in it, and be able to put a bolt and washer here as well, just for reassurance in case something were to happen to the snap ring. Having the bolt there means it still keeps the shaft retained, nothing's going to fall out. Having it double retained is better than single retained, especially over a long season. We would hate to have any match get messed up just because of a single snap ring comes off and then we can't intake. We'd want to avoid any situation like that. Okay, so that is all of the major mechanisms here. Couple things I didn't talk about before that we can. We did build in a belly pan cover setup that hopefully prevented us from getting game pieces stuck. At least we thought we did. We ended up leaving a bit of a gap over on this side that we did end up getting a cone stuck in at the remix event. So at Chesney Champs, we made a little something to cover that, and we did not have that problem again at all. And we also made a small little back door to prevent any possibility of like a cone getting stuck in on top of the battery or anything like that. So we were trying to account for any possible way that our matches could get messed up. We tried to prevent it by having any sort of guards for things like something hitting the main breaker, something hitting or another game piece landing in a game where you can only hold one game piece, anything like that. We also had LEDs running down the camera mount setup here. And so that was able to be flash yellow and purple to show our human player whether we wanted a cube or a cone. We also used them during disabled to show which controllers are plugged in. They'll flash different patterns at other times for some diagnostic things. So that's very handy to have that visual feedback. You can be staring at the robot and kind of know what state it's in or know things about the robot and be able to communicate that just through the robot. Lastly, we can talk briefly about our project to add a cube intake. So we have basically ideas that we knew we had this like space over here on this rail that we can mount a pivot pretty easily. So the max planetary and 90-degree gearbox is pretty easy to mount, and we can get a very strong pivot assembly done that way. And so then we just run a hex shaft across to a bearing holder, and we'll have some hubs that we're making. Because they do have to transfer enough torque, we're going to have some aluminum inserts that go into the 3D printed part so that we never round out the hex, where you kind of make this hexagon feature into a circle. And so it stops rotating with the hex shaft. But when you have that aluminum part that kind of presses into all of these little teeth, that should prevent that from happening. And so that should allow, when we turn this motor, we should be able to start from whatever our home position is and drive it down into a position to be able to spin a Cuban. And then we'll bring the intake down to be able to have there'll be a roller out here, kind of spinning in this way. The cube should suck up underneath it, hit the bumper, and then be grabbed by our intake. Because that was one of the things we couldn't do. We couldn't necessarily drive very fast into a cube and grab it into our this intake. It wasn't really designed to grab cubes off the floor super well. But we knew that was something we could add, so that's our project right now, just kind of getting practice, making more mechanisms, practice in Onshape. So what's left to do here is we'll figure out how to actually do a motor mount. It's probably going to be mounted somewhere over on this side of the arm. As we figure that out, we'll have a motor here, and there'll be a belt up to the roller, and so this will spin and grab in the cubes. We're also looking at doing some other designs on this. Since we have two of these robots, we have FM and AM. We might do some other redesigns to possibly work on different intakes and do some more before the 2024 season starts, so we can get more practice in actually catting mechanisms fully on the robot, doing more designs. The one other part of this that we're working through and testing is being able to, this will be bolted to the hub, and then you can undo these 6 bolts to be able to take the intake off without taking the hex shaft out or unbolting it from the pivot itself. So this is one of those things where we're trying to design for maintenance. So you should be able to basically swap the whole intake with like 12 bolts and a couple wire connections. You should be able to put on a whole new intake. Since this is something that sticks out from the robot a lot, it might get run into a wall or into another robot. So having a spare ready to go in case one of these arms cracks, or in case the roller gets damaged, and being able to swap it very fast between matches is something you want to do anytime you have something that's going to stick out and possibly take damage. All right, so I think that covers all of the mechanisms and kind of how we decided to design this robot. I think coming up next, we're going to start doing some more design explorations of other teams' robots. So a lot of teams have released their CAD from the season. We haven't really gone through them. So we'll go through a lot of it live, and we'll learn kind of how some of the other teams design and see what things we can use from their designs and understand them a little bit better as we're making more robots going forward.